Hello YouTube. In this video we're going to be discussing grouped frequency distributions as opposed to categorical frequency distributions, and kind of what they are, how to read them, and how to come up with a few basic calculations to populate the rows and columns of your table. So let's go ahead and start by defining what we mean by a grouped frequency distribution. These are distributions that are used when we talk about quantitative data types. Okay, so these are numerical data types, things like weight, height, mass, mass and weight, I guess are the same thing. Volumes, heart rate. Anything that you can count. For the most part, we use quantitative, they're quantitative data types, but we use a grouped frequency distribution, okay? And another way to look at a group frequency distribution is that maybe your data spans so much in terms of range, like temperature or something like that, that you have to split it up into categories, okay? So let's go ahead and take a look at a group frequency distribution that I have right here handy for us, but it says the following is a group frequency distribution for the number of hours that boat batteries lasted. So I know that sounds really exciting, but basically you would notice that boat batteries, according to what I've got right here, this is telling us a few things. First of all, number of hours they lasted, the shortest time was 24 hours and the longest time was 65 hours, okay? So that being such a broad span, what they've done is they've taken that data and they split it up into what we call classes. So you notice we have class limits, class boundaries, but this has 1, 2, 3, 4, 5, 6 classes is what this distribution has. Okay, so we're going to start by talking about a few things, comparing class limits, class boundaries, what we see here with the tally and frequency, and then cumulative frequency. But let's go ahead and start with this. Class limits, you'll notice that the classes here, it says 24 up to 30, 31 up to 37, 38 to 44. These are all very, very similar to what we have here for our class boundaries, except for you notice that all the class boundaries, they end in a 5, okay? So they end in a 5, and also this class limits on the first class here, we say 24 up to 30. For the class boundaries, we have 23.5, which is a half under the lower class limit is what we call this, and a half above the upper class limit of the next one here. So basically class boundaries, to determine these, what we'll need to basically accept first is this. You'll be able to give me class boundaries if you can give me class limits first, okay? So the first thing we typically seek are class limits. And other things I want to mention about the table so far in terms of class limits, class boundaries, when you look at the limits, okay, we say, all right, well, 24 up to 30 and 31 up to 37. You notice that it goes from 31 to 30 here, and it's seemingly there's like a gap, and you wouldn't want that because what if you had a battery last 30 and a half, hours? Where would you place it? Okay, so that's why we have both class limits and class boundaries. You'll notice that the class boundaries, they look like this. They say 30 and a half is the upper class boundary on my first class here, but it's also the lower class boundary of the next. So what this does for our boundaries, it serves to kind of plug up the holes here and help us decide where to classify data that would fall in between class limits. Okay, so it's important to note when you read the class boundaries of a table, this first one says here you'll include data between 24 and 30, but the class boundaries, you read it as this, 23.5 hours up to, but not including 30.5 hours, okay? So there were some raw data before, this table was made. But we have made this table, and basically, you could see how organizing this into a frequency distribution would be nice. You could see from the tally instantly that most batteries fall in these 3 classes here. So we say like 38 to 58 hours. If I was a consumer, I could expect that to be the case. And I can also see that being represented here in our frequencies. These are the higher frequencies occurring in here. Okay, so a lot like categorical frequency distributions, you get your tally, you get your frequency for each class. And then last but not least, our cumulative frequency. I just want to be clear on how you calculate these, but cumulative frequency, it's kind of like saying your frequency up until now. So by the time we got up to a 30.5 hour, kind of datum, we said we had counted 3 total batteries up until this point. But when we get to the cumulative frequency, cumulative means up until now kind of thing. We have 4 because what we've done is we've taken the original 3 and we've added on now the 1 that we've gotten for this class. So basically, it's like answering the question, how many batteries lasted up to 37.5 hours? Well, 4 up until now because you had the initial 3 and then this one here. So to find this cumulative frequency, you just keep running through it. You say, well, 9. Well, 9 is the sum of the 5, the 1, and the 3, or basically the 5 and everything below it, okay? So you have 9, and if you were to add on this other 9 right here, now you're up to 18. If you were to add on this 6 right here, you'd be up to 24. If you add on the 1, you get up to 25. Okay, so this is our group frequency distribution. Kind of how to read a little bit. Let's point a few things out here that are very important. So starting with this, number 1, there should be about between 5 and 20 classes. You notice this, back here had 6 classes. But basically, 5 to 20 classes, you get anything over 20, it tends to be a little bit overwhelming to read it. But under 5 is a little bit underwhelming. You can't draw many conclusions from it, okay? Number 2 here, the class width should be an odd number. So now class width is something we haven't talked about yet. And I do want to point out this is just a suggestion on number 2, but we're going to practice this. Class width is how wide each class is in terms of like how many data are in each class. When you look at your class limits up here, take into consideration our 24 to 30. Here we say 24 up to 30, we'll include in the first class. We say, well, how many data are here? And a lot of people like to tell me the width. They say, oh, well, the width is equal to 6 because it spans 6 units because 30 minus 24 is 6. But if you write these out, you can say 24, 25, 26, 27, 28, 29, and 30, and actually count them up, you're saying, well, 1, 2, 3, 4, 5, 6, 7. So it's not 6, it's actually 7. So one thing that's important to talk about here is class width. Before we get into why it should be an odd number, is you calculate it by, you could take your upper class limit for a class and subtract off the lower class limit of that same class and then just add 1 to it. So for example, 37 minus 31, that's 6, plus 1 makes it 7, which is actually how many data are there. So class width measures how far apart or how many data fit into each category. Another way to calculate class width is to subtract the boundaries for each class. So for example, that same first class there, if we took 30.5 minus 23.5, you would actually get 7. So my recommendation is always just subtract boundaries for a single class to find the class width. But we should always want this to be an odd number. And I just want to bring this up. The class width up here is 7. What if we had our first class go from like 24 to 31 instead of 24 to 30? What I'm saying here is the class midpoint would not be a whole number. And so we're going to learn what the class midpoint is here. But basically, the class midpoint is the average of these two numbers. So you could say 24 plus 31. And when you sum these and divide them in half, in other words, divide by however many there were, okay, we get 55. When you divide this by 2, what you'll see is if you have an even class width, these two numbers always add up to an odd, and when you split that in half, it's bad news bears, because now you're getting 27.5 is your class midpoint. That's not a whole number. We don't want this, okay? Number 3, the classes need to be mutually exclusive, okay? So they don't overlap. You'll notice up here that our class boundaries here, we don't ever overlap. Mutually exclusive is a fancy way of saying if you have two sets, they don't ever cross. That's not like a Venn diagram where you have these two sets overlapping here, okay? So you look at your class boundaries and none of these overlap each other. Number 5, the classes have to be exhausted. In other words, all data in the set has to be represented. So I know that this went from 24 up to 65, but basically they had to go up to 65 to cover all of the data. You couldn't say, well, there was a battery in here that lasted 80 hours and just leave it out because it's way up here on the end. You'd actually have to create a class that maybe has nothing in it just to get out to that 80 that you need, okay? And last but not least, all the classes have to be an equal width, okay? Otherwise, you'll get distorted data. So essentially, if you look at the class width up here, we say each of these classes had a width of 7, okay? So like 24 up to 31, that's plus 7. I'll change colors here, plus 7. 31 up to 38, we're adding 7. 38 up to 45, we're adding 7. 45 up to 52, we're adding 7. Okay, so answer a few questions here. Class limits are different from class boundaries because class limits are whole numbers and they have gaps. Okay, we class boundaries, we say no gaps. Okay, and then they go out an extra half value, okay, on each of our measurements from our class limits. And then also this, how does one find class boundaries from class limits? This is a good question. Going back to the table we have over here, again, just remember you take your class limits and you'll shave a half off the bottom class limit, the lower class limit, and you'll put a half onto the upper class limit. And then we have this pattern that carries out here, okay? How wide is each class? Are they all the same width? They should be the same width. As we said over here in our suggestions, and the classes are all width 7 in this case. And how do we calculate class width? Okay, well, let's take a look at, actually I think I outlined this here. Class width, okay? I guess we'll put it on here. Class width is always equal to the upper boundary minus the upper boundary minus the lower boundary would be our class width there. Okay. All right, so a few things. Class midpoint, we'll get to this more in the future when we make our own, but to calculate a class midpoint, and this is always represented by x sub m, not just x, but we average out the upper and lower boundary for a class. So for example, in this last table over here, we say we could take 24 and 30 and average them, which is what this is saying to do. Take the lower limit and the upper limit and average them. So the class midpoint for our first class there would be 24 plus 30 all over 2. In other words, 54 over 2, or 27. And all this is saying is it's kind of like the numerical midpoint between 24 and 30. So, if we were to calculate class midpoints for all of these, we say x sub m, this would have a class midpoint of 27, which is perfectly between 24 and 30. 31 and 37, if we average these, we say 31 plus 37 all over 2 is we get 68 over 2 is 34. So our class midpoint here would be 34. And we could keep doing this throughout. One thing I do want to point out, though, is this. You'll notice from 27 up to 34 here, it's gone up by 7. So you could just keep adding 7 each time. We say this would be 41, and 41 is between 38 and 44. And you could add 7 to that. You say 48. 48 is between 45 and 51. And then, just keep adding 7. Say 55, 62. But those are class midpoints and how we calculate them. In terms of the classes being mutually exclusive, not overlapping, I just want to give a quick example here. These are two different sets of classes, but we say this is correct on the left. Correct on the left. Incorrect. Incorrect on the left, because you'll notice here that the 10 to 20 and then 20 to 30, if you had somebody age 20, say on the survey, whose class would you stick them in, the first or the second? You can't have overlapping here. So when we talk about limits here, we say 10 to 20, that'd be more appropriate. This is the correct version on the right side here. And then 21 up to 31, you notice, by the way, they all have the same class width. You'd say 20 minus 10 plus 1 is 11. And then 31 minus 21 is 10 plus 1 is 11, or you could say 10 up to 21 is 11, 21 to 32 is 11, this is 11. Okay, and then last but not least, equal width. We just want to make sure that all classes are equal width. This is only to provide you with a little bit of information. Sometimes you have what is called an open-ended distribution. Open-ended distribution would be something like a survey. If we gave here, we say all the classes are the same width. This is kind of what we borrowed from over here. But you notice we said 65 and above. And so that would be an instance where we just keep it open on that one there, and then we can get a number of minutes to go with it. Or actually, this is a different example, age in minutes. Minutes we could say below 110 minutes if we were measuring some sort of physical activity. So just a little bit about group frequency distributions.